Assalamu alaikum. Can you all hear me? Am I audible to everyone? Yeah. Okay. So just a minute, and I'll share my screen and then start. Okay. So is my screen visible to everyone? And is the screen clear? Like the resolution and stuff? So I hope so. Okay. So is the screen visible to everyone now? Okay. So let's start. Okay, so the topic of today would be DC circuits, and we'll be doing some basic questions or some questions such that they would outline most of the theory or whatever concepts are required to solve most of the questions related to the topic. Okay, so the first question is in front of us, and the question is figure 5.1 shows an arrangement of three resistors, a 20 ohm resistor, another 20 ohm resistor with a 40 ohm resistor in parallel. So calculate the total resistance of this arrangement. So the way to do is I divide this into two sections. One section would be this, and the other section would be this. I need to add the resistances of both these sections. So R1 plus R2. I'm calling this R2, this whole thing, and I'm calling this whole thing R1. And that's my total resistance. It's equal to this. My total resistance is equal to. Okay, so that's what my equation comes out. And now what I do is simply R1, the resistance of this R1, this pink arrangement is simply 20 ohms. And for R2, I need to find some stuff. So R2 would be equal to the formula for when we add resistances in parallel is R total equals 1 over R1. Like we just keep on adding those resistances. Right now, R1 and R2 might confuse you, so I'm not writing it. So if I use the formula, I'll get 1 over 20 plus 1 over 40, both these resistances to the power minus 1. Because this was initially supposed to be minus 1 here. So instead of that, I put a power there. And now I calculate this further. So I'll get 2 over 20, 2 over 40 plus 1 over 40 to the power minus 1. And when I add these, I get 3 over 40 to the power minus 1, which is equal to 40 divided by 3. So that's the resistance that I get. So I just simply add it to the previous part, 40 divided by 3. and this will give me the total resistance, which will come out to be 33.33 ohms. So this would be my resistance, 33.33 ohms. And obviously, when you're answering CIE questions, you don't need to write the answer in four significant figures. I just did it right now, but you're not supposed to do this. Two significant figures would be enough, but I would suggest writing the answer in three significant figures, which would be very sufficient. Like, so 33.3 ohms would be fine. Okay, so this would be the total resistance of the resistors in this arrangement. Now the next part, the arrangement is connected to a DC power supply. Voltmeters are placed across the resistors as shown in figure 5.2. There is a current in each resistor. Compare the readings on the voltmeter on the 3 voltmeters. There is no need for any calculation. So just by looking at this, I need to compare the readings on the voltmeter in all these three resistors. So can someone tell me anything about this? Like, what would there be different readings on voltmeter 2 and voltmeter 3, or which one would be greater and which one would be less? Can someone tell me about this? Anyone having any idea? uh, to answer stuff, you can use the mic as well. You could type it in the chat box as well. Like, feel free to interact however you want. So yes, you're not. No one knows the answer, so that's why no one's responding. So I'll just tell it myself. Okay, so the thing with parallel circuits is combinations in parallel. This 20 ohm resistor and this 40 ohm resistor, they are combined in parallel. The arrangement is parallel. So the thing with parallel arrangements is that the voltage across them is the same. So the potential difference across the 40 ohm resistor would be the same as the voltage across the 20 ohm resistor. So this is something I know. So V2 would be equal to V3. So this is something we know because the arrangement is parallel. Now the other thing is V1. So is V1 greater than V2 and V3, or is it less than it? So that's like the thing I need to know. Okay, so if you all can recall the formula for potential divider. So the formula for potential divider is Vx equals Rx divided by R total times V total, where R total, RT is the total resistance of the circuit, VT is the total potential difference across the circuit, and Vx and Rx are the potential difference and resistance of the circuit that we need to find out. So that's what we know. And also another way to do this could be, yeah, so this is how we're supposed to do this. Now, what we do is we compare the resistances. We compare the resistance of this thing, which is 20 ohms, and of this combination. The resistance of this whole combination, I just found it out before, and it came out, sorry, not 33, and it came out at 40 over 3. So this was 40 over 3, and 40 over 3 is 13.33. So the resistance of this whole part was 13.3 ohms, which is 40 over 3. So I know the resistance. Now just by looking at this and using it in, okay, so someone, Ali, is asking me to explain the formula for potential divider. So I'll just do it. So the formula is basically that RT and VT are the total resistance of the circuit, and VX and RX are the resistance and the potential difference of that very specific component or the resistor that we need to find. We'll either know the potential difference or we'll either know the resistance, and through that we'll be able to find the voltage. Now I'll apply it so you can. Now when I will apply it, so you'll better understand, I guess. But I'll just move on, and then I hope it will become clear to you as we proceed. Okay, so we now know the resistances of both these things. And obviously, by experience or by doing this question or by doing similar questions multiple times, I can just simply tell by looking that the potential difference across the 20 ohm resistor would be greater. So that's something I could tell. And but how I get to that, I'll prove that to you guys as well. So the thing is, this formula. So if I talk about this component V1, so I'm naming this component V1 and naming this whole thing 2. So if I talk about the potential difference across V1, that would be equal to the resistance across V1, which is 20 ohms, divided by the total resistance of the circuit, which is 33.3, times the total potential difference. I don't know it, but let's say it's VT. So this is what I get. Now, if I talk about the second component, this resistor, the two, the one in red. So better if I use pen, red pen as well. Okay. So V2 equals 13.33 is the resistance of this part divided by the total resistance, which is 33.33 times the total potential difference. So when I do this, now you all just should compare. Consider Vt to be a constant. If Vt is a constant value, obviously I can just simply tell by looking that this V1 would have a greater value. So that's how I know. So Saira is asking, how did we get 33.33? We just found it out in the previous part by adding up the resistances. I know the resistance of this resistor, it's equal to 20 ohms, and I know the resistance of this blue part, it's equal to 13.3 ohms. And how 13.3 ohms? I use this whole working to find it out. So that's how I get 20 and 13.3. I add them both, so I get 13.33. Okay, so I was asking that, sir, this means that V2 and V3 is having less resistance than V1, as V2 and V3 are in parallel? Not necessarily. They have less resistance because this value here is coming out to be 13.3, which is less than 20. That's the reason. It could have been possible that although they were connected in parallel, their resultant resistance could have been, let's say, 25 ohms. That's also a possibility. So let's say if this resistor was 50 ohms and this resistor was, let's say, 100 ohms. So obviously in that case, this total resistance which was coming out for these two wouldn't have been less than 20 ohms, would have been greater than V1. So that in that case, they would have had a greater potential difference across them. So I have this part to say to you. Do let me know. And by the way, I would request you all to, whenever you ask stuff, so do send messages which everyone can read, so everyone is aware of what you're asking me. Okay, so okay, sirs. That means for making sure we need to find the readings. Yes, you need to find the readings. You need to do it. That's like a better way. So in this part, they're asking me to, without any calculations, meaning I don't need to find the actual values of these voltages. And obviously I can't do them as well because I don't know the total potential difference. But just by using other reading which I've taken in the previous part, I can simply tell the potential difference across V1 would be way greater than the potential difference across V2, V2 and V3. Okay, so similarly, the next part, and this part, the circuit in figure 7.1 includes an ammeter, a 6 ohm resistor, a length of metal resistance wire, and three 1.5 volt cells connected in parallel. So that's the arrangement which you all can see. State one advantage of using cells in parallel rather than using a single cell. So there could be multiple advantages for this. One advantage could be if, for example, one of the cell fuses, like cell runs out and has no, like, the cell stopped. So still we could get the same potential difference. And another reason could be that if we're connecting too many cells in parallel, so obviously when we're connecting multiple cells in parallel, they last longer because each cell is now providing a little amount of current. So there's some reasons involved, but when you like combine cells in parallel, they'll last longer. So I have this part displayed to everyone. So the next part, the potential difference PD between points P and Q in the circuit of figure 7.1. Potential difference between point P and Q. So obviously, if this is point P and Q, so what would be the potential difference across this point? This is an arrangement in parallel. So we know that the arrangement, when it's parallel, they have the same potential differences. So this whole would have obviously also been 1.5 volts. So that would be my answer, 1.5 volts. So that's what I just write. The next part, the ammeter in figure 7.1 reads 0.075 ampere. So this is the reading of the ammeter. Calculate the resistance of the resistant. Calculate the resistance of the resistance wire. We now need to find the resistance of the resistance wire. Okay, so I know the current in the circuit. The current is equal to 0.075 amperes. And one thing that I also know that if the circuit is series, the same current flows throughout the circuit. So the same current would be here, would be here, and would be here. So if the ammeter is reading 0.075 amperes, that reading is constant throughout the circuit. So this is the circuit that I know. Now I've also found the potential difference across the circuit, which is also equal to V equals 1.5 volts. So this is the potential difference that I know. Now if I apply this formula, V equals IR. So if I use V total, the total potential difference across the circuit would be equal to the total current across the circuit times the resistance, which would be the resistance of the total circuit. So these are some things that I know. If I could use this to find the total resistance of my circuit, because I need to find it in order to find the resistance of the wire. So I do this and I rearrange my formula and I get RT equals VT over IT. And this gives me 1.5 divided by 0.075. Can someone tell me the answer for this? RT would be equal to, okay, so RT, I just found it out, RT would be equal to 20 ohms. So I just use this 60, no, not 60, it would be equal to 20. I just use this formula 1.5 divided by 0.075. I just did this. Now what I know is I know the total resistance of the circuit. So the total resistance of the circuit, I just found it out. The total resistance throughout this region, it would be equal to what? 20 ohms. And if I talk about these components, so my total resistance would have been equal to the resistance across component 1 plus the resistance across component 2. And what are my component 1 and component 2? This is my component 1 and this is my component 2. So I'm kind of like back tracing this question. In the previous question, we knew the resistance of both the components, and through that we found the total resistance, and from that we found the current. We could have found the current. In this part, we knew the current, from that we found the total resistance, and from that we're using it to find the components, the resistance of individual components. So this would have been my formula, right, for the total resistance. So now I know total resistance equals 20. R1, they've given me the resistance, it's equal to 6. And R2, I don't know. And that's what they're asking me to find, the resistance of the wire. So R2 would simply come out to be equal to 14 ohms. So that will be my answer. And I'll write 14 ohms here right now. So is this part clear to everyone how I did this? Like anyone who's having any confusions, feel free to ask in the chat. And what about others? From where? Till where did you like get the part? Which formula? Uh, did you get how we found the total resistance of the circuit? Okay, so we have the total resistance of the circuit, which is equal to 20 ohms. So if I look into this circuit, and if I just ask you to find the total resistance of this, so I have two components in this circuit. One is this, and the other one is this. And if I ever, and if I asked you to find the total resistance of the circuit, you would have said, since they are in series, I simply add up their resistances, and R1 plus R2 would have been equal to the total resistance of the circuit. So this is something I know. Like this is something very like you get till this point, right? How I got this formula. It is simply that I'll get to that again. I'll repeat it, but okay. So if you got this, it's 6 ohms. R1 is 6 ohms. I know the resistance. I don't know the resistance of R2, and I do know the total resistance. So R2 comes out to be 14 ohms. Okay, so Ali is asking why cells in parallel last longer. So the reason is because the total current of the circuit. What's the total current? It's 0.075. And if I just ask you about parallel circuits, if I ask you about, I'll now erase some stuff because the diagram is becoming a bit tedious. Yes, Ali is also right. And actually, the reason is because in parallel circuits, there's a current flowing in this from this part, I, 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 and all these current would have been equal to the total current of the circuit. So if this is 0.075, the individual currents in all these components would have been 0.025, 0.025, and again 0.025. So that would have been the current coming out from each batteries. So now if I talk about power, so I know power equals V into I. Okay, so this is only for Ali or someone who actually wants to know why cells in parallel last longer. So now the potential difference across the battery is 1.5, and the current is very less. It's less than it would have been in the case of in the case of just a single cell. So the current got reduced, so the power got reduced. So now we conclude with Ali's statement that the energy transferred per unit time by each cells is less. So it's divided between the number of cells. So that's why cells in parallel last longer. So I hope this is clear to everyone. Clear, Ali? Okay, so there were two Alis. So Ali Kashif was asking the question and Ali Jawad was answering. In case someone is confused. Okay, so the temperature of the metal wire increases. State and explain the effect of this temperature increase on the ammeter reading. So we do know now one of the first thing that should come to your mind is if the temperature is increasing, the relationship is no longer valid. So the relationship between voltage and I is no longer valid because Ohm's law is not applicable anymore. Ohm's law stated that voltage is directly proportional to current as long as the temperature is constant. So the temperature is now increasing. So if the temperature has increased, this relationship is not valid. And what we know is that when the temperature of a metal wire increases, its resistance increases because the ions or the atoms, the metal ions, start moving more vigorously because of the increased temperature, because of the increased energy, and now they like start opposing the flow of electrons more than they were opposing before. So my current increased all of my resistance increased all of a sudden, and if my resistance has increased, so the total resistance of the circuit would increase, and once the total resistance of the circuit would increase, the potential the current would decrease because current is inversely proportional to the resistance. So the greater the resistance, the lesser the current. So my resistance increased, and due to that my current decreased. So current decreases would be the answer. Current decreases would be the answer. Okay, so now there's this another question, but we'll you all can have a look at it. But I'll take a 10 minutes break for Isha prayer, and we'll resume at about 9:10 or 9:12:13 inshallah. Assalamu Assalamu alaikum. Can you all hear me? Okay, good. So let's resume. So there's this question. Explain what is meant by electromotive force. So EMF is the energy converted from non-electrical to electrical form per unit charge, or the energy required to drive a charge through the whole circuit. So both are correct definitions, and you could write both of them, and you'll get the 2 marks. So the next part, which is like the proper part we're going to do, part B, an 18 ohm resistor and a 30 ohm resistor are connected in series with the battery. State the relationship between IB in the battery, the current I1 in the battery, the current I1 in the 18 ohm resistor, and the current I2 in the 30 ohm resistor. Okay, so if you're clear on your concepts of series and parallel circuits, so we do know that in series circuits, the current is same throughout the circuit, and this is a series circuit. So if this is the current I, it would be same throughout the circuit. So I could just simply write that. So I could simply write that IB equals I1 equals I2. So this is something I know. Now the next part, said an equation that relates the EMF E of the battery, the potential difference V1 across the 18 ohm resistor, and the potential difference V2 across the 30 ohm resistor. So I now know that EMF is E, and I do know that EMF is equal to the potential difference across the circuit. So this is the relationship which I know, E1 equals V1 plus V2. So this is how I do it, and I hope this part is clear to you, because this is like one of the essential concepts of DC circuits. How does the potential difference and current relate in a series circuit? Calculate the current in the battery. Now I need to find the current in the battery, which would also be the same as the current in the whole circuit. So what's the total resistance of my whole circuit? The total resistance of my circuit would just be the sum of this 30 ohm resistor and this 18 ohm resistor. So the total resistance would have been 48 ohms. And what's the total potential difference across my circuit? I know that it will be equal to 12 volts, which is the EMF of the battery, because this is equal to Vt. And then I can just simply equate the formula. V equals IR, and similarly Vt equals IT RT, or not RT, just I, because I is the same. So now I just use this formula, and I make my equation I equals Vt over RT, and I just get Vt is 12, total potential difference is 48, and I get my current, which turns out to be what? Can someone tell me the answer? It would be 0.25 amperes. 0.25 amperes would be the answer. Now, now I need to find the potential difference across the 18 ohm resistor. So now again use this formula V equals IR, but this time I'm not using total voltages nor the total resistance. I'm not using that. What I'm doing is V1 equals I times R1. So like this is just an example of how the same formula could be used in two multiple ways. So depending on what my total resistance is, I'm getting what my resistance is. If is the resistance of the total circuit, or is the resistance just of a single component, the potential difference is coming out accordingly. So this is something important. Do keep that this in mind. So I'm getting this formula V1 equals I1 R1, and I becomes equal to, or sorry, I do know what I is, and I do know R1. So the resistance across this resistor is what? This becomes equal to I is equal to 0.25, which is the current throughout the circuit, throughout everything. All the components, both the components have the same current, and so does the battery. 25 times R1, which is 18. So I get, I think, 4.5 volts. I think it's 4.5 volts. Just verify something. Yeah, 4.5 volts. And then the calculate the power produced in the 18 ohm resistor. So power has a simple formula. Power equals IV, and I is 0.25, and voltage is 4.5. So this will give me something around 1.125 watts, I think. The resistors obey Ohm's law. State Ohm's law and describe one limitation on this law. So Ohm's law is that my voltage is directly proportional to the current in the circuit, and the limitation is that as long as the temperature is constant, just exactly what was validated, like what the assumption that was violated above in the previous part. Okay, so next part, the resistors are made from the same material but have different cross-sectional areas and different lengths. Set the relationship between the resistance R and the length L of a wire of cross-sectional area A, the resistance R and the cross-sectional area A of a length of a wire of constant length. Okay, so we all know the formula, and if you don't, like, write it somewhere, this is the formula for resistance. And from this, I can tell resistance is directly proportional to length, and similarly, resistance is inversely proportional to area. So this is just how I write it. The next part, set the color on the bands of the 30 ohm resistor. Okay, so what I know is that the first band represents the first digit, second band represents the second digit, and the third band represents 10. What would be the power of 10? Like times 10 to the power of x. So this tells me the power of x, the value of x. So the first thing, the first band is supposed to give me 3. The second band is supposed to give me 0. And the third band is supposed to give me 10 to the power 0 because I just need a resistance of 30 ohms. So now I look at what values would be suitable for this. So 3, the number suitable for 3 is orange. So the first band is supposed to be orange. And then 0 is suitable, like 0 gives color black gives me a value of 0. So this would be black, and so would this be black. So this is just simply how I do these questions. So I hope this part is clear to everyone. Okay, so moving on to the next part. A 4.5 volts battery is connected in a circuit with an ammeter, a light dependent resistor, LDR, and a 1800 ohm fixed resistor. Figure 7.1 as a circuit diagram. Okay, Yusuf, which part do you want me to repeat? The resistor one? So there's a resistor of resistance 30 ohms, and they're asking me to tell them the color codes of this resistor. So obviously there are three, actually four bands most of the resistors, but right now our resistor has 3 bands. So what we know from from our understanding of the 3D is that the first band tells us the first digit of the resistance, the second band tells me the second digit of the resistance, and the third band tells me the power of 10, which with this value should be multiplied with. So if it's a 30 ohm resistor, the first band should give me a value of 3 because I need 30 ohms, right? So 30 ohms would be equal to 30 times 10 to the power of 0. This is what 30 ohms would be equal to, because 10 to the power 0 would be equal to 1. So the first band should have a value of 3, the second band should have a value of 0, and the third band should have a value of 0 as well. Like I get these values accordingly. This tells me this comes from here, first third band. The second digit comes from the second band, and the first digit comes from the first band. So this is how I get these digits. So 30 times 10 to the power 0. The fourth is, if there's a fourth band, then it's about tolerance. But they won't, it's highly unlikely they would ask you, but that's about the tolerance, like a plus minus value through which the value, like if it's plus minus 4, let's say, then, or 5, let's say, then this should mean that the resistance is 30 ohms. But when I'm practically building these circuits or making them, the value could vary between a range of plus and minus 5. So it could vary between 25 to 35 ohms. So that's the tolerance. So I hope this is clear to you, Yusuf, to you as well. Okay, so now the next part is calculate the total resistance of the circuit. Obviously, the resistance of the LDR is 9,000 ohms, so I just write it here, 9,000, and total resistance of the circuit. So the total resistance would be 1 over R1 plus 1 over R2. times, and this whole becomes inversed. So 1 over 1800 plus 1 over 9000 inverse. Can someone tell me the answer? Okay, so my answer would come out to be 1500 ohms. So this would be my answer, 1500 ohms. So the total resistance of the circuit would be 1500 ohms. Now, one thing to note, like one thing you all should keep in mind is that whenever there are two circuits involved which are combined in parallel, the total resistance of this combination would always be less than the individual component, the resistance of the individual components. So 9000 and 18,000, the resultant resistance should be lesser than 1800 and 9000. So the resultant resistance should be always less than 1800, which is the lowest resistance. So it's always supposed to be less than 1500. So that's why I'm getting a total resistance of 1500 ohms. Now the reading on the ammeter. So for that, I simply again apply the formula VT equals I T times RT, and I equals PT divided by RT. So the total voltage across this circuit is 4.5 and the total resistance is 1500. So my voltage comes out to be 3 times 10 to the power negative 3 amperes, which I could also write it as 3 milliamperes. So this is how you do it. Why I put inverse in the brackets? Uh, okay, by the way, you should try asking the questions and like general questions that everyone can read, because other might often get confused as to what I'm answering. Okay, so the reason is because the formula was 1 over RT equals 1 over R1 plus 1 over R2. This was the formula for the resistance of a parallel circuit. How you sum them up. So to write this, if I inverse this thing on both sides, if I inverse it on both sides, I simply end up with RT equals 1 over R1 plus 1 over R2 inverse. So this kind of helps me in my calculation when I need to put the values in the calculator. So that's why I did this. Otherwise, there is no other reason. So I hope this is clear to you. A very bright lamp is switched on and the light intensity on the LDR increases. So if the light intensity on the LDR increases, what happens to the resistance of the LDR? When the light intensity increases, the resistance decreases. So if the resistance has decreased, so what would happen to the current in the LDR and what would happen to the current in the 18 ohm resistor? Okay, so you don't need any calculations to answer this part. You can just simply answer it by just observing what's being done here. So just a second. Okay, so if there is something like this is my current which is flowing in the circuit. Okay, so this is the current which is flowing, and this current is supposed to get divided in two parts. One would be I1, and the other one is supposed to be I2. So this would be how the current would divide. Now, when the current starts to divide, the current chooses the path where the resistance is the least. Wherever the current would find the least resistance, more current would flow through that path, and where the current would find greater resistance, less current would flow through that path. So if there was 9,000 ohms resistance of 9,000 ohms through this region, this part or the second component, and this resistance all of a sudden decreased. So now there was less resistance, and the current I2 would increase because there is less resistance there. So I2 increases. And similarly, if I2 has increased and uh, yeah, so that's why I2 basically increases. So like that's what happens. Okay, so the next thing is what happens to the current in the 1800 ohm resistor. So the current in the LDR obviously increases. So this is something we know. What now happens is that the total current of the circuit, what happens to the total resistance of the circuit, if obviously the resistance of this LDR 9000 ohm resistor decreases, what happens to the total resistance of the circuit? Would it decrease or would it increase? Anyone? Okay, so basically what would happen is that this current started to get divided between I2 and I1, and obviously there was now more current flowing through I2, and the total resistance of the circuit has decreased. So obviously, if more current will be flowing through I2, there would be less current flowing through I1, and the current in I1 would decrease. So the current in the 1800 ohm resistor would decrease. Okay, so I hope that part is clear to everyone. Okay, so moving on to probably the last question we'll do today. So, still, what is meant by potential difference across a resistor? So, potential difference across a resistor is the energy dissipated from electrical to non-electrical forms when a charge passes through the component, through the resistor. Calculate the current in the 40 ohm resistor. So, I know that the total potential difference across the 40 ohm resistor is 9.6 volts. So, if I do know that, I could say, and I'm naming these components 1 and 2. So, I know V1 equals I1 R1. So I just need to find I equals V1 over R1. It would be equal to 9.6 divided by 40, and I'll get 0.24 ampere. So this would be the current. And then part 2, B part 2, calculate the EMF of the battery. So EMF of the battery, uh, okay, so I now know the current. It's 0.24 ampere. And I could also tell the total resistance of the circuit, because if it's a series circuit, the total resistance would be just the sum of both these resistances. So it would be 10 plus 40 ohms. This would be equal to 50 ohms. 50 ohms would be the total resistance of the circuit. So it's, if the total resistance is 50 ohms, I need to find the total potential difference, which is equal to the EMF. V equals IR, and IA is 0.24 times 50. So I think as Elias told, the answer would be equal to 12 volts. So 50 times 0.24. Yeah, 12 volts would be my answer. So that's how I get the answer. Now the student has three different voltmeters to measure the potential difference across a 40 ohm resistor. These are labeled 0 till 2 volts, 0 till 20 volts, and 0 till 200 volts. Each resistor each has a pointer that shows the potential difference on a scale. So it will explain which of the three voltmeters is best to use to measure this potential difference. So which one would be the best to measure a potential difference, uh, which is equal to what? Which is equal to 12 volts. So which of these would be best for it? This resistor, which is 0 till 2 volts, obviously I cannot find the voltage with it because it's greater than its maximum value. And now the two resistors which could actually give me an answer would be the 20 volt 0 till 20 volt or the 0 till 200 volt resistor. The 0 till 200 volt resistor, although it could give me the answer, but it would have a very large scale. So maybe if it's something as big as this, so the readings would have been, this would be 10, this would have been 20, this would have been 30. And if it were a 0 to 20 volt resistor, the readings would have been in such a way that maybe this was 0, this was 10, and this would have been 20. So obviously I could just simply tell by looking that the range, or the way I could tell this, the more accurate or the more precise value I could get, the more precise reading that I could take from which one of these, the 0 till 200 or 0 till 20 volt, it's the 0 till 20 volt voltmeter, which would give me a more, which will enable me to take a more precise or more accurate reading. So that's why I go with it, because the range in that 20 0 to 200 volt voltmeter would have been very great. Calculate the power produced in the 10 volt 10 ohm resistor. So I now need to find the power produced in the 10 ohm resistor. So the 10 ohm resistor, I know the total current in the circuit, which is equal to 0.24, and I also know the resistance across that resistor, which is equal to 10 ohms. So I could just simply use the formula power equals I square R, and this would give me 0.24 whole square times R, which is equal to 10. So this is supposed to give me the answer, and I think Ali has answered it. So it will come out as 0.576 watts. Now the next part is a bit important. The student has available two 10 ohm resistors with power ratings of 1 over P and 2P. So these are the two resistors. Power rating of P and 1 over 2P. So this is the value of P. P is equal to 0.576. So P would be this, and 1 over 2P would be the half of it, which would be equal to 0.288 watts. So this would be 1 over 2P. Suggest why a resistor with a power rating of 1 over 2P is not suitable for the circuit in 10 part 1. So the reason why it would not be suitable, as Ali has answered, is because the circuit has a current of flowing which is 0.24 amperes. Part C again. Okay, so I will get to part C, but let's just complete part D for now. Okay, so the student has the power across this resistor is uh, 0.576 ohms. That's a watts. That's the power it is generating. So if I suddenly use a resistor with a power rating of 1 over 2p, it cannot the maximum power that could go that could be dissipated from that resistor without it burning is 0.288 watts. But if I start dissipating a power of 0.576 watts, it would just simply burn. So the answer is that 1 over 2p resistor will overheat and eventually burn. So that's the answer. And coming to part C, explaining it again. So I have three resistors, 0 till 2 volts, 0 till 20 volts, and 0 till 200 volts. So the 0 till 2 volts resistor is a very less resistance, very less like the maximum range of the 0 till 2 voltmeter is very less. My maximum reading would go on till 12 volts, so it can't measure that reading. So 0 till 2 volts is out of the question. The next two resistors are possible. The 0 till 20 volts the next two voltmeter, I don't know why I'm calling it resistors again and again. The 0 till 20 voltmeter and the 0 till 200 voltmeter both can give me the answer. But my readings, if you see, the reading is 9.6 volts, and that's what the 40 ohm resistor is like to measure the potential difference across the 40 ohm resistor. So if I use the 0 to 200 volt resistor, the accuracy or the precision of that component would have been very less. Because if I talk about the scales, so if it's a 0 till 20 volt resistor, so the values would be very much spaced apart, and I could simply easily tell this is 9 and this would be 10, and I could also locate the value of 9.5. But if it were just a resistor with 0 till 200, if this was the case, so in that case this would have been 100, this would have been 50, and 10 and 20. So you see, I cannot accurately observe readings. I cannot accurately observe a reading of 9.6 volts on this. So I can't do it accurately. And that's what they've asked me which of the voltmeter is best to use this potential difference. So that would be the best resistor. Uh, Although both can do the work, but the best one would be the 0 till 20 volt. Okay, so Sam was asking that can you please explain part two? I don't get why it overheats. Okay, so the thing with resistors is the resistors are dissipating heat. What are they doing? What's the potential difference? Potential difference, or like for example, take the example of a light bulb. So lamp. So when you pass current through the lamp has a potential difference, and what it actually does is it dissipates the electrical energy into light energy and heat energy. Similar would be the case with the resistor. The resistor would be dissipating electrical energy into heat energy. It would be converting it into heat and dissipating it into the surrounding. Now A resistor of a rating 1 over 2p, which is equal to 0.288 watts, would mean that the maximum heat that it could convert, like the maximum power that it could convert from electrical to heat energy, is 0.288 watts easily. If the power exceeds beyond this point, the resistor would start to overheat and it would eventually burn. So that is what the reading tells me. It cannot dissipate power beyond this number, 0.288 watts. But what the thing is that it's connected in a circuit where the current is 0.24 ampere and the its resistance is 10 ohms. So obviously its power would always be equal to this value, 0.576. So since it's now dissipating more energy than it can easily do, so it would overheat and burn. So just like the case with the fuse. So the thing with fuse is whenever the current exceeds in the fuse, so the current exceeds, the fuse overheats and it burns and stops the current circuit. So that's what the case is here right now. So I hope this is clear, this part. I hope it's clear this time. Okay, so now this part, the next part is a bit important, but based on what we've done, the questions we've done before, so I hope this time it could be easy. So if you all remember this part, this previous question, when I connected this 9000 ohm resistor with this 1800 ohm resistor, the total resistance of this combination was less than the resistance of the individual components. So the total resistance came out to be 1500, which was less than 9000 as well as less than 1800. So it was less than both these values. So that's what happens when we connect an arrangement in parallel. So similar would be the case here right now. If I had this resistance 40 ohm resistor and I suddenly combined a resistance R with it. So, and now if I ask someone to tell me the resistance of this region, this combination, the 40 ohm resistor and the R resistor. So obviously I can tell for sure that the total resistance of this region would be less than 40 ohms, right? Is this clear to everyone? Why would it be less than 40 ohms? This is like something we know from the questions we've done up till now. Okay. So if anyone has any questions regarding this, please do ask. Otherwise, I'll assume it's clear to everyone. So I know for sure that the resistance when I combined this resistor R with it, the total resistance of this decreased. So this is something I know. Now what happens is the total resistance of the whole circuit. What would happen to it? The total resistance of the circuit would be equal to this region, which I'm calling 1, and would be equal to the sum of this region and this region. So if I talk about the total resistance, it would be equal to R1 plus R2. So since and before this 1 ohm resistor was there, before I had connected this, before this was connected, there was a value of 40 volts. And now when I connected the resistor R, the value suddenly of this component 1, this region 1, decreased from 40 ohms to some a value less than 40 ohms. So the total resistance of the circuit would decrease. This is something we know. Now the next part is to find the current in the 10 ohm resistor. And I know that the current in the whole series circuit is the same. And if the total resistance of the circuit has now decreased, what would happen to the current in the circuit? If the total resistance of the circuit decreases, the current would increase. Right? This is the formula V equals IR. So if the total resistance increases, the current would decrease. So the formula for current would be current equals V divided by R. From this, I can tell that current is inversely proportional to resistance. If the resistance of the total circuit increases, the current decreases. And right now, okay, so right now the total resistance of the circuit has decreased because uh, I hope this is clear because the resistance of region 1 has decreased from 40 to some value less than 40. So the total resistance of the circuit has decreased and it's inversely related to current. So current would increase. So current increased. And why did the change occur? The change occurred because the total resistance of the circuit decreased and current was inversely proportional to resistance. So this is something I know. The next part, potential difference across the 10 ohm resistor. Now I know one thing for sure is that the voltage across the current across the 10 ohm resistor suddenly has increased. And I know the formula that V2 equals I R2, that the voltage across component 2 would be equal to the current time the resistance of the component 2. So the resistance of this component 2 or the 10 ohm resistor was the same, and all of a sudden the current across it increased. So the current has increased, the potential difference would obviously increase. So that's the relationship, that since V is directly proportional to I, so since current has increased and the resistance was constant, the voltage, the potential difference increased. So the answer for this would be increase, that the potential difference across the 10 ohm resistor increase. And now the next part is, if I talk about the EMFs. So I know for the EMF that EMF equals V1 plus V2, and the EMF has a constant value. So let's say EMF had a value of 12 or something, I'll get back to it. And EMF had a value of 12 and initially, and now what happened is V2 has increased. V2 increased and E remained constant. So how would the change affect it? That V1 is supposed to decrease. So V1 would decrease. So V1 is the resistance across this region 1. And by parallel combination, we know that whatever is the current across this whole thing would be potential difference across this whole thing. It would be the potential difference across the 40 ohm resistor as well as the potential difference across the resistor R. So the total potential difference of this 40 ohm resistor would decrease because V2 has the potential difference across the 10 ohm resistor has increased. Since this increases, this would obviously decrease so that the total EMF of the circuit remains constant. So for example, let's say that before I did this, V1 was 5 volts and V2 was, let's say, 7 volts. Let's just assume it for the moment. V2 was 7 volts and V1 was 5 volts. Now, and the total EMF was 12 volts. Now what happened is that V1 uh, increased. V1 increased from 5 to, let's say, 8 volts, and the total EMF still remains remains constant, which is 12 volts. So what would happen to V2? Obviously, V2 is supposed to decrease. It would become 4 volts, so that the total sum is again equal to 12 volts. So obviously V2 decreases. Uh, so sorry, by the way, I messed this up a little bit. V2 has increased right now. So V2 has increased from 7 volts to, let's say, 9 volts. So V2 has increased. So obviously V1 would decrease and it would become something less, 3 volts right now, for example. So that's what happened, and that's why the answer for this would be decrease. And the reasoning would be because the PD remains same and the potential total PD remains the same, and it has increased across the 10 ohm resistor. So I hope this part is clear to everyone. If anyone has any questions regarding this, feel free to ask. By the way, this is where we'll end. So just ask if anyone has any questions to ask, or otherwise, we'll end the class for today. Okay, so I guess it's clear to everyone. Okay, so we'll inshallah meet tomorrow. So tomorrow would be a short class. I'll just do some questions regarding radioactivity, and then if anyone has any questions regarding the syllabus and stuff, you can ask them. Okay, so till then, assalamu alaikum.